Hello everyone and welcome to lecture. In this lecture I'd like to go over a couple more advanced ways of determining whether or not an improper integral diverges or converges without evaluating the actual integral itself. Because it turns out that there's actually many situations in which the integrand function could be very complicated and not possible to evaluate nicely by hand or even using a computer. So we have these nice comparison theorems called the direct comparison theorem and the limit comparison theorem, which allow us to go through and actually determine very often whether or not an improper integral diverges or converges without even evaluating it. So you'll remember that we defined the definite integral, or you should have seen the definition of a definite integral in your Calculus 2 course, so your previous calculus course. But I reviewed this in the previous lecture, and the previous two lectures. And the main idea here is that in these previous two lectures, we really went over the classification and examples of improper integrals of type 1 and improper integrals of type 2. So these were the previous two lecture videos. And essentially, what this does for us is it tells us how to properly evaluate an improper integral. So that information can be found in those lectures. Essentially, a type 1 improper integral is where either of the two bounds goes to positive or negative infinity, and or possibly the third case is where both of the bounds stretch infinitely long. And an improper integral of type 2 is one where the function itself is discontinuous. So subtype 1 is where it's discontinuous at the left boundary point. Subtype 2 is where it's discontinuous at the right boundary point, and subtype 3 is where it's discontinuous at some point C inside the domain, in between A and B. And for both cases, both major types of improper integrals, we've seen that dealing with each of these cases is very similar. We have to use limits and be very well versed in our integration procedures for calculation from Calc 2. So it's really good to review as many of those as possible and as many examples as is possible for you to go through and consider. But so in this lecture, one of the big things that we're going to consider and we're going to look at is the following. So we're going to consider two different methods for determining convergence or divergence of an improper integral without evaluating the improper integral. And these two methods are called the direct comparison theorem or the DCT for short, and the limit comparison theorem. Or LCT for short. And so before we do this, before I write down the actual words and definition of the direct comparison theorem and the limit comparison theorem, what I want to do is go through and actually evaluate the integral, the improper integral of a relatively simple function that is going to be very useful for us for applying the direct comparison theorem and limit comparison theorem. So we're going to consider the following two examples when we're going through. So for this first example, we want to look at the integral from 1 to the infinity of the function 1 over x to the alpha. And we want to ask ourselves, for what values of alpha does this integral converge? For instance, will it converge if alpha is 1? Will it converge if alpha is 2/3? If alpha is 5/4? Right? We want to kind of generally figure out what values of alpha this will converge. And we're doing this because this is going to be very helpful when we're doing these comparison theorems. We're going to use the results that we're getting here when we apply the comparison theorems. This is the motivation for why we're doing this. But so we know that this is going to be the same thing as the limit as b goes to infinity of the integral from 1 to b of 1 over x to the alpha, or x to the negative alpha dx. And what I should do is be very specific here. So we're just going to consider alpha between 0 and positive infinity. So positive values of alpha. And well, we know that we're going to have different results here for differing values of alpha. Specifically, this integral right here, move this over a little bit. So if alpha is not equal to 0 or not equal to 1, then we can just use the power rule here. So the antiderivative of x to the negative alpha dx is going to be 1 over negative alpha plus 1, so 1 minus alpha, times x to the 1 minus alpha plus c. This is if alpha is not equal to 1. If alpha is in fact equal to 1, then the antiderivative is just the antiderivative of 1 over x dx. Because when alpha is equal to 1, this is just x to the negative alpha is just 1 over x. This is the natural log of the absolute value of x plus c. And so because of that, this limit, the answer to our problem is going to split into 3 parts. Well, when alpha is not equal to 1, it is between 0 and 1. This is going to be the limit as b goes to infinity of, and we know that when alpha is between 0 and 1, this is going to be 1 over 1 minus alpha times x to the 1 minus alpha. So from this, when we plug in our endpoints here, this is going to become b to the 1 minus alpha over 1 minus alpha minus 1 to the 1 minus alpha, which is just 1 divided by 1 minus alpha. And because b is, 1 minus alpha is positive because alpha is between 1 and 0, so 1 minus alpha is also positive. This limit is going to be positive infinity. It's going to diverge. Likewise, when alpha is equal to 1, we're going to get the natural log of b minus the natural log of 1, which is just natural log of 1 is 0, but the limit as b goes to infinity of the natural log of b is also positive infinity. So when alpha equals 1, the improper integral of 1 over x to the alpha from 1 to the infinity also does not exist. It diverges to positive infinity. However, this final case where alpha is strictly greater than 1 is going to yield for us something very nice. When alpha is strictly greater than 1, 1 minus alpha is going to be a strictly negative number. 1 minus alpha will be negative, and therefore the limit as b goes to infinity of b to the 1 minus alpha will be 0. This limit goes to 0 as b goes to positive infinity. So to summarize our result here, we have that this integral diverges to positive infinity when alpha is between 1 and 0, when alpha is equal to 1, but when alpha is strictly positive, or strictly greater than 1, the value of this limit is going to be 1 over alpha minus 1, which is a neat result in and of itself. But this characterizes for us, for any type of function, whether this improper integral is going to diverge or converge. So for instance, if you were to see the improper integral from 1 to infinity of 1 over the square root of x dx, with this result, you can immediately say that this is going to diverge. However, if you were to see the integral from 1 to infinity of 1 over x to the pi dx, you can say immediately that this is going to converge because of the fact that the alpha value here is strictly greater than 1. So you can see how powerful something like this is. This gives us a general approach now to essentially compare more complicated functions to these simple functions, simple exponential functions, which is why it's so useful for us. In exactly the same way, another important function to consider is the function 1 over x to the alpha, but now on the interval from 0 to 1, not from, it's not an infinite interval. So this is now 1 over x to the alpha on the interval from 0 to 1. This is still an improper integral. It's type 2 subtype 1 because the integral, or the function 1 over x to the alpha is never defined, or not defined at x equals 0. So this is the limit as c goes to 0 from the right of the integral from c to 1 of 1 over x to the alpha dx. Again, just like before, we kind of have to break this into multiple different parts. For alpha between 0 and 1, for alpha equal to 1, and for alpha greater than 1. So the antiderivative of this function, 1 over x to the alpha, is the same function as before. So the antiderivative is the same. It's going to be 1 over 1 minus alpha times x to the 1 minus alpha. So evaluated at the upper bound of 1 here, this is just going to give us 1 over 1 minus alpha, and minus, it'll be c to the 1 minus alpha over 1 minus alpha. And when alpha is between 0 and 1, 1 minus alpha is positive. So because of that, this limit is in fact equal to 0. And the value of our integral, the answer for this integral is going to be 1 over 1 minus alpha. Whereas for the other two, well, for the first one, we have natural log of 1 minus natural log of c. And this goes, well, negative times natural log of c goes to negative infinity as c goes to 0. So when we multiply that by negative 1, this entire thing right here diverges to negative infinity. And likewise, even when alpha is positive, we're going to have here 1 over 1 minus alpha for our upper bound, the antiderivative, and the lower bound is going to be, again, c to the 1 minus alpha over 1 minus alpha, which, because 1 minus alpha is negative when alpha is greater than 1, the limit of this as c goes to 0 is going to 1 over 0, which diverges to positive infinity from the right. So the main result here is that this integral, 1 over x to the alpha, from 0 to 1, converges when alpha is between 1 and 0, and diverges otherwise. This means if you were to write down something like, say, the integral from 0 to 1 of 1 over x to the pi, you could immediately say, using this theorem, that this diverges. However, if you were to write something like the integral from 0 to 1 of 1 over the cube root of x squared, from this result right here, we can say immediately that this converges, because this is the same thing as the integral from 0 to 1 of 1 over x to the 2/3. And because 2/3 is an alpha that's between 0 and 1, and we're integrating from 0 to 1, this we can say from this result that this must converge. So really what we've just done is show for a very wide class of functions convergence and divergence. And you really want to note the comparison here between the improper integral of type 2 and the improper integral of type 1, right? This example, we're using the same function, 1 over x to the alpha, but when we change the domain that we're integrating over, in the first case from 1 to infinity, in the second case from 0 to 1, the actual intervals in which alpha give us a convergent improper integral change as well. Right? For the second example, for our type 2 example from 0 to 1, the range in alpha is from 0 to 1. This is the convergence range, and then from 1 onward, or alpha greater than 1, we have divergence. Whereas we had the exact opposite case for 1 over x to the alpha on the interval from 1 to infinity. And so to explain this, and really kind of give you a graphical feel for what's going on here, I did a little plot here of the function 1 over x to the alpha for varying values of alpha. I just did for alpha from 0 here, all the way down to 0, up to 2, right? So this is the function 1 over x to the alpha for whatever this alpha value is. 1 seems to be our critical alpha value, so I just chose that as the midpoint here. And you're just seeing me change the value of alpha and show how that changes the function. And what's neat here is that the connection between the improper integral of from 0 to 1 and the improper integral of from 1 to infinity of this function is that as we change alpha, we're seeing that the function gets closer and closer to the respective axes. So we found that for alpha from greater than 1, So like alpha equals, say, 1.62 right here. The improper integral from 1 to infinity converges, but the improper integral from 0 to 1 diverges. So I'm going to stretch out my bounds here all the way out to a large value, and then I'll stretch C all the way down here. So you see that for values of alpha greater than 1, 1 seems to be this critical threshold where at 1, neither this improper integral from 0 to 1 converges, or the improper integral from 1 to infinity converges. But if we just push past 1 a little bit, even to 1.04, say, or 1.01, then this improper integral, the green improper integral here, is going to converge, and the orange improper integral is going to diverge. So at 1, they both diverge. But if we push away from 1, the green converges and the orange diverges. Whereas if I push to the opposite direction here, so we have 1 as our kind of midpoint here for that alpha, in this case both of the improper integrals diverge. If I make alpha slightly smaller, maybe like 0.82 here, then this improper integral from 0 to 1 of the function of type 2 will converge, and this green improper integral will diverge. So I think this is a pretty neat demonstration, just kind of generally showing what it is we did here. And the reason that we're looking at this is for a very specific reason. We're going to use these alpha functions to compare in the limit comparison theorem and the direct comparison theorem when we write those down. So without further ado, let's get in and start actually writing down exactly what it is the direct comparison theorem says. We'll do an example of the direct comparison theorem, maybe 2 examples, and then we'll write down the limit comparison theorem and do an example or 2 of that. So this is the direct comparison test for improper integral convergence. We're going to assume that f and g be 2 continuous positive functions such that f of x is always bounded below by g of x. This is for x between some a, so above some a, and infinity. I should also state that this is the direct comparison test for improper integrals of type 1. It can be stated word for word, or almost word for word, the same for improper integrals of type 2. I'm not going to write this down, but it's very, very similar, and the idea behind it is similar. Mainly, we have 2 conclusions from this theorem. If the improper integral of g of x from a to infinity converges, then the improper integral from a to infinity of f of x also converges. This is basically saying that if we have a complicated function f of x that we don't want to compute the direct integral of, the improper integral of, if we can find a simpler function, a function that's simpler to integrate, that's always above f of x, then that converges, then the integral of f of x must necessarily also converge. And likewise, if the improper integral from a to infinity of f of x diverges, then the integral from a to infinity of g of x must also diverge. The second statement is saying that if we have a complicated function g of x, maybe, that we don't want to calculate the direct improper integral of, if we can find a simpler function that's always bounding g of x below, we call this f of x here, that has a divergent improper integral, then the improper integral of g of x must also diverge. So let's see a direct example of this. You could be asking, does the improper integral from 2 to infinity of the function t times sine squared, or how to x times sine squared of x over 7x to the fourth minus 5 converge or diverge? This is, we're going to use the DCT here to figure out whether it converges or diverges. So we know that the function f of x here is this function. And we know that this function, x times sine squared of x over 7x to the fourth minus 5 is would be a relatively complicated function to go through and get the exact integral of. It's always positive though, so we know this is always greater than or equal to 0 for all x on the interval from 2 to infinity, because we have sine squared here. So this will always be positive, and the x will always be positive, and so will this as well. 7 times x to the fourth minus 5 will always be positive on this interval. And we also know that this will always be less than or equal to x times 1 over 7x to the fourth minus 5. Because the sine function is always bounded above by 1. Furthermore, for values of x in this domain, we know that 1 over 7x to the fourth minus 5 will always be less than or equal to 1 over 7x to the fourth minus 5x to the fourth. Because 7x to the fourth minus 5x to the fourth will always be a smaller number than 7x to the fourth minus 5. So we're dividing by a smaller number here, which means 1 over this quantity will always be greater than or equal to this quantity right here. So 7x to the fourth minus 5x to the fourth is the same thing as 1 over 2x to the fourth. So we have that complicated unknown function, which we don't want to calculate the direct integral of, is this function right here, this will always be less than or equal to x over 2x to the fourth, which is the same as 1 over 2x to the third. So this is our comparison function, g of x. And we know that the integral from 2 to infinity of g of x or the integral from 2 to infinity of 1/2 times 1 over x to the third converges from the previous example This is an example of an improper integral from 2 to infinity where the alpha value is greater than 1. So then because this converges by the direct comparison theorem, the improper integral from 2 to infinity of x times sine squared over 7x to the fourth minus 5 must also converge. And there you have it. We've proven something mathematically about the improper integral of a very complicated function using a much simpler integral. And this is the heart of this direct comparison theorem. So if we go ahead and plot this out, I'll show you exactly why it is this is working, graphically speaking, and also how we kind of want to think of this procedure when we're doing these types of problems. So this right here, the purple curve right here, is a graph of the function x times sine x squared over 7 times x to the fourth minus 5 from 0 to b, where b can be any positive value that we want. And let me stretch this out a little bit so we can kind of see a little bit better how this function is in fact a very complicated function. It's going up and down, up and down, up and down because of that sine function going from 0 to 1, 0 to 1, 0 to 1. And so if we were to compute even the normal integral from 0 to b, it'd be a relatively complicated thing to do, let alone computing the limit of this as b goes to positive infinity. Yep. So the point here is that calculating the exact value of this improper integral is not necessarily something that we want to do. So instead of doing this, we're finding a function that is directly above this function. We actually use an even simpler function when I did the example just now. But here I'm just going to graph out the function that's immediately above it, which is x over 7x to the fourth minus 5. This is also a relatively straightforward integral to go through and evaluate for the improper integral. And this green area right here is the easier test function. And we know that this converges, so you can go through and try and do this yourself with this different test function than the one that we use, which is x over 7x to the fourth minus 5. You can go through, get the exact value of this definite integral, and sure enough, it's going to converge to a nice value, a finite value. And so then from the direct comparison theorem, because this green area is finite, it converges. The orange area, which is the more complicated integral area, also must converge. So we're saying that this green area is kind of trapping and forcing this orange area to become finite. So this is a very neat application and a good example problem to show why the direct comparison theorem is working the way it is. Specifically, right, in this example, we use the direct comparison theorem part 1. Just to be specific here. So let's see this for one more example. Does the improper integral from 3 to infinity of 4x to the 1/3, the cube root of x, over 5x plus the square root of x dx converge or diverge? And I didn't do this first step on the previous problem, but sometimes a useful test to kind of start off seeing whether you think it's going to converge or diverge is to test when x is large. This is for improper integrals of type 1. For improper integrals of type 2, you test when x is close to the point of discontinuity. But I want to point out here that we're not applying the theorem yet. Alright, this is just to kind of test, to kind of see and get a feel for whether or not this is going to converge or diverge before we apply the test. And I want to note that when x is large, we're going to have that x is much larger than x to the 1/3. So for very large values of x, when x is large, we have that our function 4 times x to the 1/3 over 5x plus the square root of x. Oops, sorry, I meant here not 1/3, but the square root of x. This is going to be approximately equal to 4x to the 1/3 over 5 times the x, because this 5x is much, much larger than the square root of x. It's for large values of x, it's dominating the denominator. And this is then 4/5 x to the 1/3 divided by x, which is 1 over x to the 2/3. And we know that the improper integral of this function right here diverges because it's one of those alpha type intervals where alpha is less than 1. It's 2/3 right here. So the integral of this from 3 to positive infinity is going to diverge. Now again, I want to point out very heavily here that I have not done any convergence tests here. This is not good enough for proving the divergence of our integral. It just gives us some sort of an idea of what we should expect when we actually do apply this test, and very often is a good rule of thumb for doing something like this is a good practice to kind of figure out whether or not you expect the integral to converge or to diverge. So let's see here how to actually go through and actually apply the direct comparison theorem. From the test that we did before, we see that this is probably going to diverge. So now we have to go through and test. And in order to do that, what we're going to do is take our function, right? And because we expect it to diverge, we're going to look for a lower bound to our function. And we're going to directly use the fact that x is greater than 3, and the fact that when x is greater than 3, function x itself, is always going to be greater than square root of x. And this is going to help us get an upper bound, or sorry, not an upper bound, a lower bound to our function. because 1 over 5x plus root x will always be greater than or equal to 1 over 5x plus x. The reasoning behind this is that the square root of x is less than x itself, and therefore 1 over the square root of x will always be greater than 1 over x. So this is the reasoning behind there, and why in the denominator there, the square root of x, or the denominator 5x plus square root of x, that 1 over 5x plus square root of x will always be greater than or equal to 1 over 5x plus x. And this is great because it really simplifies our comparison function. In the denominator there, it becomes a 6 times x. And in the numerator, we have 4 times x to the 1/3, which simplifies down to 2/3 times 1 over x to the 2/3. And what we've shown now is that a lower bound for our unknown complicated function that we don't want to get the integral of is this 2/3 times 1 over x to the 2/3. And now, what's really kind of important here is that we're applying the second version of the direct comparison theorem. We're trying to show that this diverges. So we found our lower bound, our f function, and the unknown function in the second part is our g function. And the reason f of x is a good comparison function is because we already know what the integral is going to be from the example that we did at the beginning of lecture. We know that this is going to diverge because of the fact that we're integrating from 3 to infinity, and alpha, the alpha value, is between 0 and 1. So it's 2/3, which is between 0 and 1. And therefore then, by the direct comparison theorem, we can state that the integral that we started out with, which we don't know the actual value of, must also diverge, because it's always bounded below by this comparison function whose integral is divergent. So let's see a graphical visualization of this similar to before. Here we have two separate functions, the green function and a purple function. The green function is the complicated unknown function that we started out with, and the purple function is the comparison function of 4 over x to the 2/3, or 4 over 6 times x to the 2/3. I'm just going to change it to 2/3 just so that it exactly matches up with what we did. But essentially what we've shown is that because the lower function diverges, the integral of it diverges, so its improper integral diverges, meaning it has infinite area under the function. Because the orange area diverges, the green area must also diverge by the direct comparison theorem. So this is really cool, and is a direct graphical illustration showing that this theorem is actually working very well. It works out very well to show what we want to show. And I'm just changing here the bounds. The lower bound should be 3, not 2. So this is matching the problem. So I want to go over one more final example of the direct comparison theorem. And this is going to be a very interesting geometric example. Right? The previous two examples have been purely mathematical examples. But I want to close this portion of the lecture, which is the direct comparison theorem portion, with an example that I think is very neat because it's very geometric and intuitive, and non-intuitive at the same time. And that might sound a little bit confusing, but it should be more clear as we kind of go along. So the first thing that I want to do is consider the main function that we're going to be using in this example, and this is called the standard 1 over x function. And using this function, right, we're going to produce a very special shape, which is called Gabriels Horn. So 1 over x is 1 over 1, which is just, put this right here, is the point 1, 1, and the function y equals 1 over x very quickly decreases down to 0 in the limit. So this is the curve y equals 1 over x. And in your Calculus 2 course, you'll hopefully have seen a number of different surfaces of revolution, which are surfaces that you get when revolving a given curve around a given axis. So in this case, we're just going to consider the surface of revolution that we get when we revolve the curve y equals 1 over x around the x-axis. So the resulting shape is going to look very similar to this, where the cross sections of this shape are circles. So this is what we get when we revolve around the x-axis here. This is my best drawing of it on with pen and paper, but I guess a visualization will probably be very, very much more helpful here. So I'm going to switch over to my GeoGebra 3D window. I've been using Desmos so far up until now, but I'll use GeoGebra 3D to visualize this. So here's the GeoGebra 3D window with a plot of the function y equals 1 over x. It's this green curve right here, and it's in this plane right here. I have a third axis there because I want to demonstrate what you get when you revolve this curve around the x-axis. So when you revolve this curve around the x-axis, we do that, we get this shape right here, and this shape is a shape called Gabriels Horn because it looks very much like a horn. And what we're considering is Gabriels Horn specifically, which is the infinite shape that you get. So if you go along the x-axis here to positive infinity, so all the way to positive infinity along the x-axis. So what we're going to do is we're going to consider both the volume and the surface area of this three-dimensional shape. And we're going to come to a very interesting conclusion about these two geometric quantities. So you'll hopefully recall from your Calculus 2 class the applications to surfaces of revolution. And we're now specifically going to apply those formulas to Gabriels Horn. So in general, the formula for the volume of a surface of revolution is given by the integral from a to b. If you're going to say from here, it's a to b right here. The volume of, say, this segment of the surface of revolution is going to be pi times the function squared. So the volume for the full Gabriels Horn is going to be the improper integral from 1 to positive infinity of pi times 1 over x squared dx. Because we're interested in the volume of the full Gabriels Horn from 1 to infinity, this formula can just be justified in the sense that we're taking the integral of the cross-sectional area, the cross-sections being circles of radius f of x. So we know that this is the limit as b goes to infinity of 1 to b. The pi will come out because it's a constant. This is now just the integral of 1 over x squared dx. And we already know from our previous example that this is going to be a finite value. It's going to converge to a finite value because we're integrating 1 over x to the power alpha, where alpha is greater than 1 on an interval from 1 to infinity. However, just for the sake of this problem, I'll go through and do this integral out for you. We know that the antiderivative of x to the negative 2 is going to be negative x to the negative 1 plus c. This is what the antiderivative of this function is going to be. So this is going to be negative x to the negative 1 evaluated at b and 1, or pi times the limit as b goes to infinity of 1 over 1 minus 1 over b. And the limit as b goes to infinity of 1 over b is 0. So the volume here is just equal to pi, which is very cool. Our volume is equal to pi, and that means that Gabriels Horn, the infinite Gabriels Horn, contains a finite amount of volume. So we've computed the volume of this surface, or of the volume contained within the surface, and it's this finite value of pi. And now we want to go through and look at the surface area of this surface of revolution. So just like this formula for volume comes from standard Calc 2 course, the general formula for surface area of a segment, so say this segment from A to B, also comes from Calculus 2. It's the integral from from A to B of 2 times pi times the function times the square root of 1 plus the derivative of the function squared, which admittedly is a little bit more complicated than the function for volume. But it's still exact, and it still makes sense to talk about this, especially even in terms of just the cross sections themselves. And I can go over with where this formula comes from with you in office hours if you have questions about it. But the main idea here is that we're going to directly apply this formula to compute the surface area of Gabriels Horn. So it's the integral from 1 to infinity of 2 times pi times 1 over x times the square root of 1 plus the derivative of f here is going to be the derivative of 1 over x, which is negative 1 over x squared squared. So the integral that we have to evaluate, the improper integral that we have to evaluate, is the integral from 1 to infinity of 2 times pi times 1 over x times the square root of 1 plus 1 over x to the 4th. And this is an admittedly very complicated integral to evaluate. We don't want to go through and directly try to evaluate this by hand, even though you could go through and try and do that. Instead, we're going to use the direct comparison theorem. And we know that this 1 plus 1 over x to the fourth will always be greater than or equal to just 1 itself. So by the direct comparison theorem, then, this integral will always be greater than or equal to the integral from 1 to infinity of 2 times pi times 1 over x dx. And this integral, as we showed in the first example that we went over today, is divergent. So therefore, this integral right here, the direct comparison theorem, must also be divergent. Which means that the surface area of Gabriels Horn is infinite, or the shape has infinite surface area. So this is a very interesting shape because it has a finite amount of volume. It bounds a finite amount of volume, but the surface area surrounding that volume is actually infinite. So if you tried to, say, use gift wrap or paint to cover the surface, you would never be able to, because this surface area is infinite, but the volume contained inside of it is finite. So I think this is a great, very interesting kind of counterintuitive example to end the lecture on. But thank you very much for tuning in. I hope you had a fantastic day and that you learned something.